junior here at MA. Okay, so I'll just jump right in. So ever since I can remember, my dad has had a habit of becoming completely captivated by certain very specific topics, usually involving math, and has often swept me along for the ride. One such topic that caught my dad's interest was Plato's theory of everything. Plato said that the dodecahedron, along with 4 other solids, were the model of the universe, but he never really explained what that meant, and that essentially is what my dad loved. It was like this grand enigma that he needed to crack. So, at a very young age, my dad gave me this little crystal dodecahedron and started introducing me to the concept of Platonic solids and nested polyhedra. Now, I don't know how well you can see this, and I actually have a larger version. But I think you might agree it's a pretty little object. And these polyhedra can be kind of beautiful in a form of artwork. But not only are they beautiful, here I'll keep holding this up so you guys can see, not only are they cool looking, but they're also special because they're tied together geometrically, so that if you choose one of them, every other solid is already there, inside that one, in a specific sequence, getting infinitely bigger or smaller. Now, this concept, at least for me, was a little overwhelming at first, because trying to understand the theory of, well, everything is small. But what I instead hope to do today is kind of teach you guys what is so special about these polyhedra in a physical and mathematical sense. Okay, so before I jump right into it, just some key terms that I think I will be using a lot during this presentation, so you guys, it will be helpful for you to know. So a polyhedron, which is a 3-dimensional shape like a cube, is constructed of, is constructed of polygons as its faces. So this is one face. An edge is a line segment where 2 faces meet, and a vertex is a point at which several faces and edges meet. Okay, so now that we've defined those, that is not what I meant to do either. That's cool. Well, the most symmetrical of these solids are the Platonic solids, or regular polyhedra. And these are constructed of polygons that are regular polygons, and each face is exactly the same. These polyhedra are known as, now let's see if it works. It's not working, that's really fun. Oh, it is, that's a tetrahedron with 4 triangular faces, a cube or hexahedron with 6 square faces, a octahedron with 8 triangular faces, a dodecahedron with 12 pentagonal faces, and finally an icosahedron with 20 triangular faces. Now, Plato's theory was that these solids represent the universe, and they represent the elements individually. So the pyramid or tetrahedron represents fire, the cube represents earth, the octahedron is air, or the octahedron is water, and the icosahedron is air. And finally, Plato associated the dodecahedron with the whole, or the cosmos. So Plato defined these originally, as I mentioned earlier, as solids that are completely congruent. They are made of congruent polygons. And about 2,000 years ago, or more than that actually, Euclid went ahead and proved that there are only 5 of these solids. So how did Euclid prove it? Well, Euclid, in his proof, starts out with a disclaimer, and I'll read that to you right now. He says that, this is roughly translated from Greek, so we'll see how this goes. So he says, "One will find in this work no diagrams. The methods that I use require no constructions, no geometrical or mechanical arguments, but only algebraic operations, subject to a regular and uniform process." Now, as fun as that sounds, I prefer to look at this in a more visual and tactile way. So that's what I'm going to do, using these fun little magnetic tiles that I loved to play with when I was like 8, and I still love to play with them, but my hands are bigger now, so I'm not nearly as skilled at using them, but we'll try our best. So just to start at the very beginning, if you have a polygon with 0 vertices, you don't really have anything at all. Same with 1 and 2 vertices, you can't really make a 2D shape out of that. If you have 3 vertices, however, I'm sure you can all guess, that makes a regular polygon, which is a triangle, and that has an interior angle of 60 degrees. So here I have my triangle. Now, if I have one triangle, I can't really do much with it by itself. How about if I have two triangles? So if I put two triangles together, I can try and fold it, but it's not really going to make anything. It just kind of folds into a flat shape again. And what I really want is to create a three-dimensional shape. So if I take three triangles and I fold them, I hope you can see that it kind of makes a three-dimensional shape that is actually a representation of one vertex of a tetrahedron. So I'm just going to put this up here for now, because they're magnetic. So we have three. We know three works. And so let's try four. Let's just keep trying them. So if we have four, again, oh no, that is not. Okay, well, see, big hands. So if I fold it again, you can see that it makes a three-dimensional representation of one vertex of an octahedron. I hope you guys can see that. So I'm going to stick that one up on the board as well. And let's just keep trying, because this has been working really, really well for us. So now I have my four again, and let's add a fifth one. Now this is where it gets a little tricky because it doesn't, okay, there we go. So I hope if you can kind of see, this folds to make a representation of one vertex of an ecosahedron. There it goes. Okay, so I'm going to stick this up on the board because it's not going to stay together with me just holding it. But, so there we have 3, 4, and 5 triangles around a vertex. And these have interior angles of 180 degrees, 240 degrees, and 300 degrees respectively. So now that we know that 5 works, let's try 6. So we have our 5, and now we have our 6. So, I don't know, I can't really fold this, which is an issue because I'm trying to make a three-dimensional shape. But does anyone have an idea as to why I might not be able to fold this? No? Maybe? Yes? I know you do.
Sure.
I'm calling on you.
Interior angle of 360 degrees.
That is exactly right. Thank you. You're so smart. Okay, so that has an interior angle of 360 degrees. And that means it will lie flat, so it can't be folded into a three-dimensional shape. And so that's not going to work. So with the same logic, if we have one square, I'm just going to move on to the next shape. If we have one square, it doesn't really work. Again, if we have 2, it doesn't really work either. If we have 3, we're able to fold that into a representation of one vertex of a cube, right? So that, I'll just add that up to our table. And that has an interior angle of 270 degrees. Add that up there. Actually, no, I want to keep that. So now that we have 3, we know that 3 works. If we add a 4th, we run into a similar issue of not being able to fold it. And again, that's because the interior angles of the 4 squares, which are individually 90 degrees, add up to 360 degrees. So you can't fold that, and it'll just lie flat. So now I can put that up there and add to my chart. All right. So, and then if you keep adding squares, you're not going to be able to create a three-dimensional shape. That just won't help you. You'll have greater than 360 degrees, and you'll be stuck. Moving on, I'm not going to walk you through this one, but moving on to a pentagon. It has an interior angle of 108, and if you add 3 of those together, you're able to fold that into a three-dimensional shape because that adds up to less than 360 degrees. And then the same thing is if you keep adding that, it is greater than 360 degrees and won't work at all. So that gives us our 5 Platonic solids, as you can see. And some of you may be wondering why we can't just keep adding vertices to the polygon that we create the shape out of. Well, that's because, let's take a hexagon, for example. If we keep adding vertices, it increases the interior angle of the individual polygon. So a hexagon has an interior angle of 120 degrees. And if you try and add up only 3 of those, it adds up to greater than 360 degrees right away. So that's not going to work for us. Okay, so now that we know how to create an individual vertex of each of these Platonic solids, let's move on to what the whole shape looks like. So starting out with a tetrahedron, this is a net of a tetrahedron, and a net is just a flattened version of what the three-dimensional shape is. And if you can see, the tetrahedron net that I have up on the board, I have a smaller version in my hand, and if I fold that up, it goes into a representation of what a tetrahedron, or what we know as a tetrahedron, is. So I'll put that down there. And then moving on to the octahedron. This is a net of an octahedron, and again, I have it right here. And you'll see that the faces on the net that I have on the board are numbered. So you can see that the octahedron, named for its 8 faces, folds up to a shape that looks like this, and that's what we know as our octahedron. And then moving on to an icosahedron. So this one's a little bit hard to fold, but just while I'm trying to do that on the fly, you'll notice that if I fold it up, right here, that's where you find that shape that is the 5 triangles that we have over here. So that's how you can kind of check that I'm doing the right thing, and this isn't actually an icosahedron. So if you can see, it folds up. It's not perfect because it's having a hard time sticking together, but that's an icosahedron. And then moving on to a square shape, that's a net of a cube, and if you fold it up, oh my goodness, it's not going to stick today. Interesting. It becomes what we know as a cube, right? And then same with the dodecahedron. Again, this is a little bit more of a complex cube because there are a lot more faces, but if you fold these together, you'll get a representation of what we know as a dodecahedron. So, woo, that was fun. Yeah, so a dodecahedron right there. All right, so now that we've looked at what each shape looks like individually, let's move on to just quantifying what we know about each shape. So you'll notice that I've numbered the faces on all of them, and I've just put it into this nice table that describes the number of edges, vertices, and faces of each of the Platonic solids. So just take a moment to think to yourself if you notice any patterns. So mathematicians always like to look for patterns and cool things. So right off the bat, I noticed that the cube and the octahedron have the same number of edges, and that their vertices and faces, the number of vertices and faces that they have, flips. Similarly, the dodecahedron and the icosahedron have 30 edges each, and the number of vertices and faces flips. And then finally, the tetrahedron, with 6 edges, has the same number of vertices and faces. So what is really the significance of this? Because now I've just kind of thrown a bunch of numbers at you. But so from this little pattern that we noticed, you get the concept of duals. And duality is a property of polyhedra. So that if you choose one polyhedra, there's a specific other solid that goes with that one. And if you choose it, you can construct it from that original polyhedra. So that's what we'll do. But first, just starting with 2 solids, or 1 in this case, a tetrahedron is dual to itself. So that's because the number of faces and vertices are the same. So you can kind of mesh it around and make them fit. And then a cube is dual to an octahedron, and vice versa. And a dodecahedron is dual to an icosahedron, and vice versa. So thinking about how we construct this dual of a specific solid, let's just take a cube, for example, because that's an easy one. So it will be constructed in the following way. First, you place a point in the center of each of the faces of the original polyhedron. You then connect the new points that you've made in the faces, and then you would erase the original polyhedron. Erase the original polyhedron, or as you see, I've shaded it in to just make it a little bit more clear. And that's how you would get a dual. And so this may be a little bit of a leap, but if you have these duals, and this is just one example, you can kind of express them in a certain way so that they all appear at once. So give me a second. I'm just going to get my So I have this. And thank you to my dad for helping me figure out how to build this. So if you can kind of see, I've color-coded the different shapes that appear here. So I hope this works. You have one tetrahedron that are all the purple ones, and then the blue, that's how they would fit together as a dual. And then you have, well, actually here you have a cube octahedron, which is like one of the stages in when you can kind of, I don't know how to explain this without showing you a graphic, which I don't have, but if you kind of expand the inner octahedron and kind of build it up so that you would then be placing the points or the vertices of the cube inside the octahedron. If you do that, it has interim stages, so this would be one of the interim stages. And if I just kind of continued this point out, it would make a cube. If I made a little triangle here, yeah. But, and also you can see that these 4 points make a cube-like shape as well. So, yeah, what is now that you kind of had a chance to look at this, what is the significance of this? Well, thinking back to all the way at the beginning of my presentation, when I mentioned Plato's theory, which was that all this can describe the universe, right? So the cool thing about this is that you can keep taking a dual of a dual and scaling it up and down so that it can describe really small things, really great things, and you can describe things as large as the universe, which was Plato's theory. So yeah, this is a GeoGebra thing, which is kind of like the model that I made, except it highlights the dodecahedron, which would actually fit around this and make like little house-shaped things on each of the faces of the cube. But if you can kind of see, and I'll scroll down here a little bit so you can see it better, that the dodecahedron, you have the 4 points of a cube, which I have over there, and if you just add this shape, oh no, okay, there we go. If you just add this little house shape, you can make a dodecahedron around it. Wow. And if I just like leave that there, I think that's a really great angle to be very confused and also see everything that I'm talking about.